Hi guys, first of all I miss you so much, and I wish to see you soon. This video to discuss seismic interpretation practicals in our course exploration methods. Okay, I will discuss some theoretical parts about seismic interpretation. After that I will throw the light on our project and how can solve it. Seismic data interpretation is more than picking, as I told you in our last session. Seismic interpretation, it is the only way to image or to know the structure or the different geology of the subsurface to understand the play of the field. Okay, what is a reflector? A seismic reflector is a boundary between pits with different properties. There may be a change of lithology. This change in lithology can cause change in impedance and so on, change in velocity of the waves or the density of the layer. This property cause some sound waves to be reflected towards the surface again, to be received by the geophone or to transmitted into the subsurface in the shape of refracted rays. Okay, to understand our data, the shooting system is the common depth point, and I will discuss it. Time versus depth, two-way time, and resolution. Okay, number one, CDP shooting, like the image at the left part. If we have the source 1, source 2, source 3, and receiver 1, 2, and 3, all of them can image this point, the same point. So the output trace will be like that. We will have a peak like that. Okay, if we connected this peak, it will form a hyperbola shape, but this hyperbola is not real, but it comes from the normal move out, as we discussed in the first lab. Number two, the two-way time. You need to know that this time of the wave is a two-way time, because the ray emits from the source and goes through the path until reaches the reflected surface and come back to me. So the time is multiplied by 2, so it's called two-way time. Number three, the y-axis of the seismic section here is by second, because it is time, two-way time. And I need to know which of these reflectors represent my target or my reservoir, or the top of the reservoir or the bottom of the reservoir, something like that. The only way to know or to recognize which time is the desired time from the well, but the well data is in depth meter, like in the picture. So to tie between well and seismic, this step called seismic 12 tie, we need to convert from the depth to time to tie the well. So number one, we will project the well at the exact location. Number two, we will convert the depth into time, and this process need velocity data, and we have types of velocity data inside the well. Number one is check shot. Number two is VSP. Number three is to construct a synthetic seismic trace, and we will discuss each of them individually in separate. Seismic interpretation guidelines. First of all, you need to check line scale and orientation. Work from the top of the section where the clarity is usually best, because the resolution is higher. Number three, distinguish the major reflectors and geometries of seismic sequences. Okay, in our okay, I will hide my picture. In our project, we have scale bar at the end of the map, and this picture represents the base map of the sections or of the fields. We need to know the orientation of the line on map and on sections. We can use the name of the line if it exists. AA dash, or to look at this short point and know how it increased from 100 to 145. You have to know the orientation of our section from here, 100 and 140. This slide to show you how the effect of start from the top and then go down to the less resolution part. Horizontal resolution, Fresnel zone, the area of a reflector that returns energy to the receiver within half a cycle of the first reflection. And as we go deeper, if I draw this relation, if I have a reflector there and another reflector deeper than it, we can conclude that we need more area than the shallower part to reflect the energy, and this is called the horizontal resolution, and we can estimate it by Fresnel zone. Vertical zone, vertical resolution, if there is any event smaller than a quarter of the wavelength of the wave, it won't be appeared on the seismic signal. Okay, our exercise data, we have inlines like EE dash, DD dash, and cross lines like AA dash, PB dash, CC dash, and we have phase map. So we have 1, 2, 3, 4, 5. We have 6 images, 1 of phase map, and 5 about the sections. Cross lines, it is lines that pass through the structure perpendicular to its strike. يعني if we have مثلا if we have fault like that, this line, seismic line, we'll call the cross line because it is perpendicular to the strike of the fault. And if we have lines like that, it will be called an inline. Okay, this is base map. The first step, is about to project our well. The well will give us the first point that we will start from it. We start from this well. This well will be projected on EE dash, and the desired depth will be 13,069. Okay, so this well projected on EE dash on 124. Okay, the step of well to seismic tie. I will go to EE dash and go to 124, like here, exactly here. Okay, and I will go down until 13. Okay, this is 11, 12, and 13. This point. Okay, this point is the starting point of specking. I will start to interpret this section EE dash from this point. So now I know that the desired reflector is the second one. I will go at the right and I will go at the left. As I told before, your picking told me that that you decided that the reflector is continuous on the right, on the left in this direction. If you go down or you go up, you suggest the change in the dipping or presence of fault or structure, something like that. So your picking is an interpretation, is not only an highlighting. Okay. Cross correlation. How to transfer your picking from cross section to another cross section or another inline or cross line. Okay. If we go back to the base map, you will find that EE dash oriented in this direction, while AA dash oriented in this direction. So this point is an intersection point between inline and the cross line. So this point is the same because it is an intersection point. So we need to find this point on EE dash and find this point at AA dash and put the two lines at this point to match them. This is called cross correlation, like this. Okay, this point we already have the interpretation on EE dash, and we have this point. So this point told us that this point on AA dash is our starting point. You need to make the interpretation like this. Okay, if I finish my interpretation there, I want to interpret the section AE dash from the structure, or about the structure interpretation. So we can find that there is a fault there and another one which may be the major one. Okay, from the structure geology, we can notice that this fault more curved and has a synthetic fault. This is the synthetic one. This is the major one, LISTRIC. So we can expect a change in thickness on the down, from the down part to the up block. So this is the down. Okay, so our peak will be there and our peak will be there. At this point, I finished the interpretation at EE dash and AE dash. So I will repeat it, this step with DD dash, where the intersection point here with AE dash. Then I will do the same with PP dash. So I started from EE dash and go to AE dash from this point to finish AE dash. Then I finished DD dash. So at PP dash I have two intersection points, or two known points. These points. Okay, if these points are projected on the same peak, that means that you make a good tie or a well tie. If not, there were a miss tie. Okay. This is called looping. Fault detecting criteria. We have 5 criteria: change in amplitude, like in figure A; change in phase, like in figure P; figure C, change in depth; change in signal to noise ratio, section D; change in offset. So any horizontal change maybe represent change in lithology, or change in structure, or change in something. This is not by chance. I will make the step of digitizing and plotting the data on the base map. Okay, digitizing. Okay, I will hide my picture. I will go to shot point, for example, 130, and go down to my interpretation, my picking, and take the value of, of this point from the y-axis. It is 13,000, and I will go to 120. It will be lower, less than 13, and so on. Besides the shot point or the main shot points, I can make digitizing for point between 110 and 120. The last step is to plot this data on the base map. I will go to EE dash at 130. I digitized all the CDB numbers in a table, so I will have a table of 130, 120, 180, and so on. Yani 130, 13, and I will write 13,000, and 120 وليكن يعني 12 مثلا 90 أي حاجة. ماشي. Okay. So at the end of this step, I will have a base map with two numbers. One of them is the CDBs, and the other one is the digitized point from the y-axis if it dips, like in our case. So I will neglect all the CDBs numbers, and I will deal with the numbers of. Okay. Finally, we are in a contouring data. You need to project the location of faults also. So we have faults there at CC dash like that, and PP dash like that, and AE dash like that. This segment is about the up, and this segment is comes from the down. of the same reflectors, and we will find that we have another fold there. Okay. I will connect all fold segments together. Sorry. This shape called fault polygon represents the major fault and the minor fault. Then I will contour the data, because the data or the fault polygon need to be the first step of contouring, because the contours will end on the fault or deal with the fault as a boundary. Okay, you will find that the data represents something like that. So the main or the best location for drilling an oil field may be there at the crest of the rollover. Shows the structure interpretation. We need to know the elements of any structure, like fault plane, fault stick, fault direction, depth angle, something like that. And for the faults, we need to know the fault axis, the axial surface that contains all the axes. If the axis is horizontal, so we have unplunged anticline or syncline. If the axis make an angle with the horizontal, it is a plunging fold, and something like that. Finally, I want to thank you for listening, and I wish it will be useful for you.